Namaskar, my dear friends. Let us talk about a PWM controller with integrated GaN device. Okay. So what we have seen earlier is we have seen a lot of like PWM controller based on like silicon MOSFET and other things, right? So as you can see, we have a PWM controller for AC/DC converter in flyback topology. Okay, and we have seen how we can drive silicon MOSFET or silicon carbide MOSFET or IGBTs or even GaN MOSFET. Okay. Now this PWM controller which we are going to discuss today is having integrated MOSFET of GaN MOSFET. Okay, so gallium nitride MOSFETs are very high efficient. That's the reason people are going or moving towards it. And you can see we have the part number which is going to be released. It is in preview stage. However, this is going to be very powerful PWM controller that you can like rely on. So this is going to be UCG28826. So what are the different applications or different things that is going to be like targeting this particular particular PWM controller is basically you would have seen docking stations and all, right? So we have docking stations which is going to give you a lot of outputs and all. Okay, it can be several kinds. There are various kinds of docking stations these days. Even we need like power supplies for monitors and also very general applications that I am trying to give it to you and these are the things that you can target for. Now once you come to the like Texas Instruments website, you will see that this is a self biased high frequency quasi resonant flyback converter with integrated GaN MOSFET. And this can handle up to 65 watts because it is having integrated GaN MOSFET. So integrated GaN MOSFET will be having limited like a current limit. That's the reason it cannot go more than 65 watts. And various parameters, if you talk about this particular GaN controller, then you can see we have operating temperature range of -40 degrees centigrade to 105 degrees centigrade. The topology that it can support is flyback topology, and it is having integrated switch. That's what I told you already. And the switching frequency it can go ahead with up to 25 kilohertz to maximum 500 kilohertz. So that's the best part of it. If we talk about some of the features that it is having adjustable current limit, like current limit can vary up or down whatever you want. It is having auxiliary less sense. It means you don't need any auxiliary like windings in your transformer. This I will tell you. Then it is having this is how like auxiliary less will save your transformer size as well. So this is going to be very small size solution. That's the reason I'm going to like discuss about this in advance itself. Like IC has not been released, however it is in preview state. And they have already developed like one evaluation module for this. For that purpose you will be able to actually like order this particular evaluation module and test your all AC/DC like adapter requirement or charger or USB wall outlets and other applications. Okay, so what we will do is today we will go ahead with the design and detail of this particular like IC data sheet, and in next session we will go ahead with evaluation module. Okay, so let us open the data sheet of this particular device. As you can see, we have the data sheet available, and this is a self-biased high frequency quasi resonant flyback converter with integrated GaN MOSFET. You can see we have 700 volt GaN MOSFET with 170 milliohm like RDS on. Okay, this is not that great. However, it is going to like meet all the spec that is needed, and it is having different modes of operation like quasi resonant mode, then DCM, CCM. Okay, like discontinuous mode or like continuous mode operations and all. Then it can support up to 500 kilohertz frequency that we have seen. So we will not talk about like all the features at a time right now. We'll talk about this little later on. This is just like, like UCC series we had seen 28C, like 38 or, I mean 48, something like that. We had seen a lot of UCC series. Similar to that, that is not having integrated GaN MOSFET or integrated MOSFETs. This UCZ series is going to have just QFN12 package with integrated GaN MOSFET. And as you can see, the targeted application is basically you are going to have USB power delivery adapters for portable electronics like chargers or adapters and all. Then we have USB power outlets and docking stations. So docking station is one of the best application that this particular PWM controller can be used for. Then we have industrial DIN rail power supplies and server auxiliary power supplies. Okay. So as you can see, very simple, like simple PWM controller that we had already designed, okay, or seen. We had the switching pin here that is going to come up like this, and simply it is going to drive that flyback topology. And the best part is you are going to get rid of your auxiliary winding in your transformer. This is going to reduce the, like transformer size and the design complexity that we face because of the one more voltage that is needed to drive this particular, like PWM controller, that is gone. So basically we have AC input. Then we have all the protections and features and filters, CMCs, all those things we are going to do, like fuse or we have MOVs, then common mode chokes, and after that HV pin is there, which is going to directly take the line and neutral input, and then we have the bridge rectifier. So as you can see, the circuit design is almost same. Only change is it is not having any auxiliary winding requirement. This is having self biased. Okay. And we have RC snubber and all those things, and this is going to go to your output section. Similar to that, we will be needing one optocoupler so that we can have an isolated design, and it will be giving you the feedback to the PWM controller IC. Okay. So we will see the pin configuration details and the design and, like methodology that is going to be used for this particular IC that we are going to discuss today. So let's get into the next page. So as you can see, this is nicely having very big thermal pad and all for, like heat dissipation, and we have the switching pin which is going to be your nothing but the drain, and similar to that ground will be acting as a source or something like that. We will see that. So let us talk about, so we have HV pin, that is your high voltage startup pin. Then we have drain pin of your integrated GaN MOSFET. We have ground. Then we have fault pin. So fault pin will be basically talking to you about, like temperatures or maybe, like all those faults that you will be having. Maybe because of increasing temperature, you might feel, you might, get into the situation of a fault condition. Then we have feedback signal. So feedback signal will actually help you to regulate your output voltage that you are going to set. Then we have turns ratio setting, like what is the turns ratio that you want to set for your NP and NS, that is your primary winding and secondary winding. Then we have IPK pin, that is your peak current and frequency dither setting pin. We have switching frequency clamp and fault behavior setting, then that is your FCL. Then we have CDX pin that is going to be having like a mode settings pin. Okay. And VCC pin is going to have ICC bias supply, which will not need external supply. It is going to just have one, like a capacitor, let's say 22 microfarad or something, we'll put it, and this is how it will be biased. And we have the ground pin one more. So as you can see, the pin configuration is quite nicely, like made with a very big thermal pad to have better heat dissipation capabilities, and all the other pins have been arranged very nicely. Okay. Good. So we have understood the pin configuration of this. Actually, this is not needed because we already know what is PWM controller and how different power supplies are designed. However, this is a new IC, so it is going to be advantageous for us to target now itself. Okay. ESD ratings and all those things are there. Let us talk about the recommended operating conditions that we are going to have. So as you can see, the continuous current that you can draw from the like drain to source of the integrated MOSFET is 4.5 amperes. So try to have less than this the ampere rating. The VCC supply will be having like a 5.2 volt to 6 volt. So in between of this only it will be there. Then we have capacitance requirement at that VCC pin, which must be 10 microfarad to 47 microfarad in between that. Okay. We have X2 capacitance requirement and all those things that we can see later on. Okay. Thermal information, this is the beauty of this particular IC, because I have not seen in this kind of packages this very small, like theta J. Okay, so the junction to ambient temperature resistance or thermal resistance is going to be 30.7 degree centigrade per watt. So for 1 watt of power dissipation, the power, like the temperature increment will be just 30 degree centigrade. Okay. Good. So this was all about this. Now let's talk about the GaN power transistor. So GaN power transistor, you can see we have drain to source resistance just around 170 milliohms, and we have output capacitance of just 40 picofarad. Okay. So this is going to be very, very small. We have GaN driver. So we have turn on dv by dt, that is your like the speed. So that is just 7 volt per nanosecond, or like it can switch on very fast. Okay. Then pick control input, like current control inputs and all we have already seen, like limiting control was there. Then we have feedback control. So RFB, pull up resistor and all these things are not needed separately. Let's get into the other features that we need, okay, for this particular device. Why we are going ahead with this particular device. So you can see about the detailed description or overview about this. So this is going to have high frequency quasi resonant AC/DC flyback converters. Okay, so with integrated 700 volt. So generally you will see like 650 volt MOSFET integrated inside the PWM controller. So they have increased the rating by 50 volt, which is going to be 700 volt primary side GaN for high electron mobility transistor. Okay. And also the frequency of operation is up to 500 kilohertz. Generally you will see either like let us say 50 kilohertz operation, or 100 kilohertz operation, or 65 kilohertz operation, but this can work up to 500 kilohertz. So this is the beauty of this particular controller. Okay, we have the like elimination of need for any LDO or something like that, because this is going to have very smooth or very like ripple free output that you want to utilize for your USB power deliveries and all. So that's the beauty. You will not need any like a separate LDO or linear regulator that will be needed. And the best part why we are going to discuss about this particular PWM controller is it is having industry first auxiliary less flyback architecture. It means you will not need any auxiliary winding in your transformer to supply the like a power supply for the USB. I mean for this particular for this particular PWM controller internal requirements. So internal power supply requirements are there, which will not require any auxiliary power supply or auxiliary windings. If you want, you can have 2 times of 65 watt nominal output, so that you can achieve 130 watt requirement. Generally these days a lot of docking stations are working with 115 watt or 130 watt application. So if you want, you can have two ICs in parallel to meet that spec. Okay. And all those X cap, Y cap, we are very familiar about it. So you can see again the same circuit is there here. Like we have input, AC input is there. Then we have like fuse. Maybe you can put MOVs here. Then we have X capacitors. We have CMC. So this is my common mode choke. We have X2 capacitor. Then we have diode for your like a polarity reverser. So we have diodes. Then we have bridge rectifier. These are the like bulk capacitors that is needed. We have filters. Okay, so then this is RCD snubber is there. Then we have, this is my transformer, and then we have the output side. This is actually called as my output like a rectifier. Okay, so you can see the output rectification is being achieved by a MOSFET. That's the like again a new technology that you can try out. Okay, and then we have the output capacitor. For output voltage regulation, we need TL431. So TL431 will be able to give you the output regulation setting, and this is the optocoupler that will be required to send your feedback regulation, so that this particular PWM controller will be able to regulate your output voltage. Okay, that's all. So we will see like once we design the complete circuit and tell you, then we will be able to talk about like timer settings or current limit setting or fault detection and all those like resistor settings, that we will do the calculations and we'll show you the circuit in our upcoming sessions. We have seen extensive design based on like output voltage regulation based on TL431. So you can refer a lot of videos that is there in our like series. So how to like select my R1 and R2, and how to select this particular R LED resistor. So this is nothing but your current limit resistor across this particular TL431. So these all things, and then this is the like RC circuit which is going to act as a filter. Okay, so this is what we have already designed. So here we are not going to discuss much about it. Okay, then you can see we have the ground pin, we have VCC bias requirement. So this is the this is the capacitor that will be needed. Let us say 10 microfarad or 22 microfarad up to, they have recommended 47 microfarad. All right, so as you can see in Turtle diagram, so if you really need like the explanation or this thing, so my main intention to show you this particular IC is to get you aware of what is the advancement that is coming into the industry with integrated GaN MOSFETs from Texas Instruments, so that you can design your AC-DC converter for docking stations and lot of other requirement, power outlet requirement or USB power delivery requirement up to 65 watts rating. So up to 65 watts rating you want to design, you can utilize this particular like GaN MOSFET controller. Okay. So this GaN MOSFET is actually inbuilt inside, so you don't have to use a separate GaN MOSFET, and the IC that you are seeing is UCG28826. Okay, so detailed pin description, if you want you can go ahead and see each one of them. So as we have already seen like various previous like videos, like what is HV pin, what is SW pin, then what is ground pin, what is my like fault pin or over temperature fault pin, we have feedback settings pin, then similar to that we have turns ratio. So what is the like a resistor value that you will put, and this will set your NP by NS. Okay, so this is how the design is also made very like digital kind of thing, you can say. Like because what happens is like it becomes little difficult for your flyback transformer design, so that is going to be easy here. Then we have peak current limitation. So peak current limit setting pin, you can do like what is the maximum current amount that you want, and accordingly you can put your resistance values. Okay, similar to that we have frequency clamp and fault responses. So for that also one resistor setting is there. So you can see each and every like features or functions that you want to include in this particular circuit design. You will need to set one resistor to do that job. Okay, similar to that we have like a mode settings and all those things like CDX, CCM, and then we have cap discharge. So all these things, what is the resistance that is required. Okay, so if you want to enable or disable based on like CCM or DCM, you can put your resistors that is needed. Then we will be having VCC input bias pin. Okay, And then we have self bias, auxiliary sensing pin, and all those things, then control. So what we are going to do now, feature description and all those things are there, so you can read about it as well. However, let's get into the next phase. So you can see this particular IC is very new. That's the reason they have explained you each and every terminologies and the valley counter, continuous valley occurrence, and all those things. They have discussed very detailed fashion everything. Okay. Coming back to the next part, like burst mode or CCM mode and all those things, like how the output varies based on the requirement or based on the design topology that is going to be used. Then you can see we have GaN switching capabilities. So how it is switching? So normal DCM, it is going to switch on, similar to that, and then switching off nicely. Okay, so you can see what is happening. It has the capability of soft start, and then we have frequency clapping and all those things. So it will not be giving you a very abrupt or any transients, so that you can avoid by incorporating this soft start technology. Okay, so soft start technology actually helps you to increase your voltage smoothly with a little bit of delays. Okay, like it will give you some little turn on time. In that case, it will be nice. This frequency dethering actually is going to help you for your EMI reduction. So that's the beauty of this particular frequency clamping and frequency dethering. So it will take around 32 steps per carrier cycle. That's the reason it is going to have a very nice switching on, switching off timings. Okay. Slew rate control and all those things are fine. Let's get into the next phase. Yes, this is a typical application that we have already talked about. So I'm not going to discuss again. A very simple, we will come up with this particular circuit design with all the values in it, maybe in our next session, and we'll show you like how it can be designed very nicely. Okay, so we'll take the reference design itself and we will be able to generate or develop this particular circuit as soon as possible for you guys. So you can see all the values and all those things are already given, and if you want you can have typical application design requirements for like notebook charger or laptop charger and all, and this is how you can develop your design. And the beauty of this particular design will be like it is going to have very small compact design. That's the reason we are actually referring this particular device. So you can see they have done one design. So their design requirement is like input voltage is going to be 90 volt to 264 volt AC. Then we have the input bulk capacitors voltage is 80 volt requirement. Okay, then line frequency is going to be 50-60 hertz both. Like you have a USA and Indian requirement both. Then we have output current requirements. So you can see 5 volt 3 ampere, then 9 volt 3 ampere, 15 volt 3 ampere, 20 volt 3.25 ampere. Okay, so any of these can be selected. So you would have seen in these days all the notebook charger or laptop charger, you can charge your mobile as well. So because this is going to select based on the requirement of the target device that is connected to the charger. Okay, so once it is laptop is connected, it will give you 19 volt or 19.2 volt or something, and similar to that other voltage levels also can be taken out. The output power, it can go maximum 65 watts. So once this power is selected, you can see it is going to be 65 watts. And output ripple is mentioned as 200 millivolts. Then we have efficiency more than 93%. So you would have seen other PWM controllers we have designed, we were achieving around 85%. Okay, so you have a significant increase in the efficiency as well. And this is how you are going to save our environment by utilizing this particular high efficiency PWM controller. The no load power is just 30 milliwatt. So 30 milliwatt is the power which will be wasted when the load is not connected. And switching frequency for the design parameter is set to be 140 kilohertz. Okay, so generally we have always designed with 65 kilohertz switching frequency or 100 kilohertz maximum, but here the design parameter is set to be 140 kilohertz. Okay, So what we'll do is, with this particular design parameter, we will discuss in our next session a complete detailed design procedure, like how each of the parameter can be incorporated into the IC design, and then we will be able to develop our AC DC converter with this particular design parameters. Alright guys, thank you.